Who has used Scala or functional programming in a creative context before? Okay, that's kind of what I expected. I ask because my talk is going to revolve around the question, how can functional programming concepts be applied to creative fields? How can we use functional programming to shape creative decision-making and creative processes? Through this talk, I'll try to give you one possible answer to this question, but I'm also very interested in hearing your possible answers that you may have acquired through your own creative pursuits. So, as a tool in this endeavor, I'm going to use the sampler instrument I developed for the Sounds of Scala library. For those unfamiliar, a sampler instrument is a type of digital music instrument that plays and manipulates pre-recorded audio samples. And Sounds of Scala is a web-based music and audio library built for Scala. I'm Johanna. I'm a junior software Scala developer. I have a background in fine arts and music production. I recently just completed my first year as a Scala developer and have been contributing to Sounds of Scala in my free time. I've also been trying to keep up my artistic practice, which consists mostly of making objects like this oil painting on folded canvas, or this public art installation I made on Lake Geneva. I also produce and perform music under my alias Iku. I've played my gigs in music and art venues across Europe, in the US, in Russia, and in Japan. And my musical practice relies heavily on the processing and layering of samples, which makes this project meaningful to me not only as a developer, but also as a musician. Now, a quick overview. I'm going to start by talking about sampling as a musical tool. I'll give you some information about the Sounds of Scala library. I'll walk you through one of the features of the sampler that I implemented using functional programming. And then we'll try and use functional programming in music composition. So we'll build a little musical sketch together. And by the end of this talk, I hope you'll have learned something about Scala or music theory. But most of all, I hope that you'll feel inspired to try out Sounds of Scala, try out the sampler yourself, and build your own little song or project with it. So, sampling. A sampler is, at the most basic level, a digital music instrument that plays back pre-recorded audio. It dates back to the 40s and 50s when experimental composers wanted to explore new types of sound, and for that they would manipulate magnetic tape. So they would cut magnetic tape, do things like reversing the tape, stretching the tape, compressing the tape, and reassembling it in order to play around with the time parameter of the audio on the tape. So essentially they were using pre-recorded audio as musical building blocks. When cassette tapes became mass-marketed in the 80s, hip-hop perfected and popularized the genre, the practice of sampling. And even today, as cassette tapes have declined in use, the practice of sampling remains fundamental to most musical genres. And in fact, modern digital samples still emulate a lot of the material processes that were once used on magnetic tapes. So you will find features to cut the sample, reverse the sample, speed up the sample, slow down the sample. So again, playing around with the audio parameter of the audio. Sampling, so using audio samples as musical building blocks, can be applied to create beats, melodies, soundscapes, sound effects, pretty much anything. And since it's such a fundamental tool in music production today, we of course also needed one for the Sounds of Scala library. I just have to drink something. So Sounds of Scala is a library designed for building web-based music applications. Its main goal is to make creating music with Scala both fun and accessible by framing, technical aspects in a creative context. And it uses a stack of Scala.js, Scala 3, and Typelevel Cats. Sounds of Scala leverages Scala.js to target the web audio API for processing audio inside of the browser, which makes it very accessible. It's not just a musical tool, it's also a way for developers to explore functional programming through the lens of music. And I'll send the link to the repo at the end of the talk in case you want to get involved. We're always looking for contributors. Now, you might ask, why Scala? Why use Scala for this endeavor? Scala is known, among other things, for its functional programming capabilities. It's not often associated, though, with creative fields. Functional programming isn't just a coding paradigm, though it's a way of thinking. And the functional style of thought isn't just great for writing clean and efficient code, it can also inspire and even shape creative processes. Now, music is emotional and sensory, but it's also structural and even functional. It fits the functional style of thought. So you can think of musical elements as data structures that can be transformed by functions. Music is also full of mathematical patterns that kind of hit the same logical sweet spot as does functional programming. So Scala's functional programming capabilities work well with the sets of mathematical patterns that are inherent to music. It allows us to express musical ideas very directly, which makes it a perfect match for such a project. Now, I think we have enough context to dive into the sampler. Depending on what sort of music you want to make, the way you will imply a sampler will be very different. The model that we're looking at today is a sampler that links samples to musical notes. So it will be a sampler that has to adjust the pitch and the playback rate to map and play a sample across a musical scale. This is useful for when you want to imitate more like melodic instruments like a piano or a guitar. And if we want to talk about repitching a sample, we first need to talk about the structure behind musical pitches. So, as I said before, music is sensory and emotional, but it's also structural. This structure becomes clear when we look at how sound and acoustics work. Musical notes and the intervals between them, so the distance between two notes, are defined by mathematical ratios. For instance, an octave follows a 2-to-1 ratio. So the octave of a note is twice as high. In order to find the frequency of an octave of a note, we have to multiply the frequency of the root note by 2. So this means that the higher note in an octave has twice the frequency of the lower note, meaning its sound wave oscillates twice as fast. An octave which is the same note but higher is an octave only because we perceive it to be the same note but higher. It's purely subjective. We perceive it as being the same note because it sounds very complete and very stable, very harmonious, almost as if it was the same thing. And this sense of stability comes from its very simple 2-to-1 ratio. Every musical interval can be broken down using these ratios, and it turns out that the intervals with the simplest ratios are also the ones that we perceive as being harmonious. This is a perfect fifth with a 3-to-2 ratio, and in comparison, a tritone with a 45-to-32 ratio. So you can hear that the intervals that have a simple ratio, a ratio that we would consider mathematically beautiful or harmonious, are also the ones that sound pleasing to us. They align with how our brain interprets harmony. I find this intersection between mathematics and the sensory experience of music fascinating. That's why I wanted to include it in this talk today. Without knowing much about music theory, we can intuitively experience the mathematical structures that are woven into music. But of course, any attempt of theorizing music and our experience of it is highly subjective and dependent on historical and cultural context. So if we use a non-Western music system, or if we descend into the abyss of microtones, terms like harmony will need to be renegotiated. In the Western music system, the smallest interval is a semitone. It's the distance between any two adjacent notes on a scale, and in frequency terms, it represents a ratio of the 12th root of 2. Using this ratio, we can calculate the frequency of any note relative to a given base frequency. In Scala, that calculation would look like this. This method calculates the frequency of a note based on its distance in steps from a reference frequency. We multiply that reference frequency by 2 raised to the power of the number of steps divided by 12. You don't need to memorize this formula, but it's just important to understand what it does, because we'll be using this same calculation to repitch our samples. And I'll walk you through how that works. Now, in our sampler, we associate our sample, here stored in an audio buffer, with a key to identify which note on a musical scale it represents. That's because we need a reference note that we can base our calculations on when we want to repitch the sample. Let's say I want to create a sampler model that sounds like a piano. I recorded C3 on my actual piano, and when I instantiate my sampler, I'll map that sample to the corresponding sample key of C3. Now let's say I want to play a C2 on that sampler, so 1 octave lower. I'll need to adjust the pitch of the sample that we map to C3. How do I do that? The way one changes a sample's pitch is by adjusting the speed at which the sample is played, which is called the playback rate. The playback rate and the pitch are always linked when it's basic sampler models like the one we're looking at today. So when you adjust the playback rate, you're speeding up or slowing down the entire sound wave, including the oscillations that determine pitch. So a faster playback rate compresses the waveform, increasing the frequency of the sound waves, and raises the pitch. While a slower playback rate stretches the waveform, lowering the frequency, lowering the pitch. It's quite literally how cassette tapes works. So if you played around with cassette tapes in the 90s and you fast forwarded it, you would have noticed a very high-pitched sort of chipmunk effect, or a more contemporary example, Nightcore remixes. Now, back to our example. We have our reference sample at C3, and we want to lower it to C2. Since it's an octave below C3, we multiply it exactly by half. Which means it will play the sample at half the speed, doubling its length, repitching it to the frequency of C2. And I think you can probably see the issue here. Since the sample length grows exponentially, pitching a sample over a large interval will quickly result in extremely long or short samples. There are techniques to deal with this, like granular synthesis, but today we're going to address this issue by providing the sampler with more samples to choose from. So we give our sampler a whole octave this time, from C2 to C3. And let's say I want to play a D2 sharp, which is somewhere in between those samples. If a sampler has a choice between several samples, we wanted to choose the one with the closest frequency to the pitch we want to play. So how am I going to go about finding that closest frequency? First of all, let's order our samples by frequency. Let's transform our map into an array of tuples containing the frequency of the note, the key, and the stored sample. And we can then use our helper function to find the sample in our ordered array with the frequency closest to our target frequency. For this, we use a binary search algorithm, so we repeatedly divide the search interval by half and compare the target with the middle element of our sorted array, which will quickly narrow down our search. So, when I want to play the note of D2 sharp on my sampler, the sampler will calculate the goal frequency of T2 sharp, find the sample with the closest frequency to our goal, divide the goal frequency by the closest frequency to get the ratio by which we have to multiply our sample's playback rate with, and pass on that ratio to the method that actually plays the sample. So the method that actually plays the sample, along with the method that loads the samples, are the only two methods that reach out into the outside world. They have to interact with the browser's audio interface. They're therefore considered impure. And so I wrapped these impure effects in IO monads to handle them in a functional and controlled way. And I asked ChatGPT to create this beautiful image about impurity for us. Now, we have a functional instrument that plays back a sampled audio across a musical scale. So let's put this to use. When we think about functional programming, we often picture an input being processed by a series of transformer functions, which then produce an output. For us, the input will be a chord or a scale, and the output will be a melody. We'll use compositional algorithms that align with functional programming principles to generate this melody. And we'll try to make it sound musical. So for this, I implemented an arpeggiator method. An arpeggiator is a musical tool that breaks down a chord or a scale into individual notes and plays them in a rhythmic sequence or in a pattern. Similar to how a prism refractors light into its component colors. Now, let's start with something simple. I have my chord progression of C minor, F minor, and G minor, and I want to arpeggiate those notes. What I'll do first is break down the chord into a list of notes, and once that's done, we can use those notes to create an arpeggio. To create an arpeggio, we basically just need to adjust a note's offset. A note's offset is the time that passes before a note is played. It's usually 0, because if I hit a key, I want the sound to play immediately. But in our case, since we have a list of notes, we don't want all of them to play at the same time. We want them to play after each other. So the offset of each note will be the current note offset with the note's length. And we'll have a listen of how that sounds. These are the chords without the arpeggio. And these are the arpeggiated notes. Okay, let's move on to something a bit more complex. Let's arpeggiate a scale. A scale is a sequence of musical notes, typically ordered by pitch and typically spanning an octave. A scale usually serves as a framework that one can use as orientation to write melodies and harmonies. So if you use the notes on a scale, they will sound, your musical piece will sound like it's part of the same universe. So they create a sort of identity for the music. I chose C minor just because I like this scale. And we follow a similar path than we did for the chords. So we call the arpeggiate method with a different set of parameters. And this time I'd like to generate a bit more of a complex pattern for our arpeggio. So I implemented Pascal's triangle. Pascal's triangle is inherently recursive, so each number in the triangle is derived from the sum of the two numbers directly above it. And in music, recursion allows for self-similar structures or repeated patterns, making the triangle ideal for arpeggios. This is the method that generates Pascal's triangle. And after that, we map the notes in our scale to the numbers in the triangle to create our pattern. So the triangle, after mapping the notes to it, looks like this. We use the same method as before to create the arpeggio. Now, let's have a listen. Okay, I think that's pretty good. I think there's too much repetition though, and I think I would like a bit more rhythm or distancing between the notes. So we're going to address both issues at the same time by filtering out a note if the note before the note was the same note. And we'll replace it by a rest, also called silence, which turns the triangle into this. And it sounds like that. Okay, I like that. Now I'd like to, build a bit of a song, so I'll combine both of my arpeggios together. I'll also reverse this sequence because I think it would be nice to have a bit of symmetry. And let's have a listen. Pascal's triangle sounds like. It might not be a Bach symphony yet, but I think it's pretty good. The fractal recursive nature of the triangle gives the melody a dynamic evolving quality, which I find interesting. And talking about Bach, there's one last compositional step that I'd like to add to our piece, and we'll use one of Bach's works as inspiration. So, Bach is known for using mathematics to generate music. He often wrote pieces of music that are almost like code that you need to unwrap in order to understand how to play them. One of those pieces is the fifth canon of the Goldberg variations. When you unwrap that piece and you understand it mathematically, you realize it's playing a piece of music on a Möbius strip, something like this. Because it uses a lot of inversions and mirroring in the melody. So, I think the Möbius strip is an excellent compositional tool for our example as well. So I'd like to use it as a demonstration of how to apply functional programming to music composition without writing any code, so just conceptually. For this, let's compose our own canon and use the Möbius strip to unwrap our own melody. Now, first of all, a canon, it's with two ends. A canon is a song where a melody is repeated by one or more voices after a short delay. So, frère Jacques, and then someone else starts. That's a canon. The Möbius strip is a mathematical object formed by twisting and joining the ends of a paper strip. It only has one side and one edge, which means if you travel along its surface, it will have an endless path and you will never really come to any end. We are going to leverage those properties of this Möbius strip to compose our canon. So, imagine we inscribe a melody along the surface of this Möbius strip, and imagine that the strip is transparent, so you can read the melody from both sides. When we play the melody along the strip, we move along its surface in a continuous loop. And when we complete one loop and return to the starting point, the strip itself will have flipped by 180 degrees due to its one-sided nature. As a result, the musical sequence on the strip will be mirrored. It will be reflected over a horizontal axis, creating a new inverted version of our initial melody. And this is what that inverted version sounds like. So the melody recursively evolves based on the physical properties of the Möbius strip, without changing its original structure. This reflects the principles of functional programming. The twist acts as a simple transformation on immutable data, and through this simple transformation, the melody recursively modifies itself. So it's kind of like a physical functional programming. I hope that's not too esoteric. Now, let's use this principle to compose our canon. Let's, like Bach, write a canon with two voices, where one is the reflection of the other. The second voice will be delayed in time to follow the traditional structure of canons. And if we once again inscribe our two voices onto a Möbius strip and play that strip, the two voices will intertwine and continuously loop, becoming reflections of each other again and again. And this is what that sounds like. And so on and so forth. It will go on forever. So in the end, you can hear that the result is pretty simple. But to get there, we used a Möbius strip and functional programming concepts to guide us in the process of composition. This serves as my example of how functional programming, even just conceptually, can be incorporated into creative decision-making and creative processes. Functional programming allows you to perceive and think in a structural way, which might come with unexpected beauty or patterns as a side effect. I hope that there will be many more examples of how to apply functional programming concepts to creative fields, and can't wait to see what people come up with. I told you I would share the link to Sounds of Scala. This is the repo, and there's my SoundCloud if you're interested in listening to my music. Thank you so much for listening.